Okay, in this video, we're going to be doing Calc BC Problem Set number 24. Problems in a playlist are in the description below. Let's take a look. Number 1, determine if the given series converges or diverges. What I'm going to do is just determine it. I'm not going to really show myself doing the work. I'm going to do the work so you can follow along. But I look at this first one, and I think it looks very weird, and I'm pretty sure it's just an integral test problem. This is like a famous sort of sequence of natural logs that you'll run into if you do enough problems. So I'm using the integral test. To use the integral test, I would assert the following is true. F of x is 1 over x, natural log of x, natural log of natural log of x is a positive function, it's continuous, and it's decreasing. Let's say from 10 to infinity, usually I just say like that. The integral from 10 to infinity of f of x dx is definitely infinity because we end up with like the natural log of the natural log of the natural log of x, and then natural log of x goes to infinity, so you're just doing the natural log of infinity ultimately. That diverges, so the series diverges. Here's what the integral ends up looking like. You're going to let u equal the natural log of the natural log of x and kind of go from there. But this is what we end up getting. Okay, so integral test on that. I don't think you would run into that in Calc BC. I mean, x, 1 over n natural log of n, definitely. That's like a straight application of the integral test. But this one's, just weird for the problem set. For B, I look at this and I immediately think I'm going to compare this to a P series. I don't think it through, so I'm going to take you through the work that I did. So I would compare this to, in the numerator, we basically have an n to the 5th, and we have an n to the 4th. In the denominator, we basically have an n cubed, and an n cubed. And I realize at this point that this is actually just the sum of 1, which definitely diverges. So I should probably do this in a slightly different way because that's not a P series. Although I could, I guess, limit compare this. It's a weird idea, like the sum of 1 diverges. So I guess you could limit compare it? I don't know. What I'm going to do instead is the nth term test for divergence. This will definitely diverge by the nth term test. So to do that, I have to show that the limit of the nth term of this thing is not 0. The limit of the nth term is, because they're polynomials of equal degree, it's just like the coefficient of the highest term over the coefficient of the highest term. You can work it out, by just looking at what's going to happen to like the coefficient of n in 2n plus 3 to the 5th and coefficient of n in 3n plus 1 to the 4th, etc. You're going to end up with a 2 to the 5th and a 3 to the 4th. You're in the denominator, you're going to get a 5 cubed, a 2 cubed, a 4 cubed. It doesn't matter what this simplifies to. It does not simplify to 0, and because of that, this diverges. All right, let's take a look at the next one. Which apparently I am just throwing out there, converges by alternating series test. I didn't edit that correctly, but that's okay. So we have the sum from 0 to infinity of -1 to the n. It alternates, so I'm immediately thinking alternating series test. -1 to the n over quantity n plus 3 to the 5th. So on its own, 1 over, not alternating, but 1 over n plus 3 to the 5th would converge by limit comparison to 1 over n to the 5th. So this actually converges absolutely, but I'm using the alternating series test, so I need to make sure that it meets the 3 criteria. So the first one is that it needs to alternate, which it definitely does. The second criteria is that the terms need to decrease in magnitude, and they do. And then the third criteria is that we need that limit of the nth term to equal 0, which it is. And so this converges by alternating series test. Alternatively, you could say this converges absolutely because 1 over n plus 3 to the 5th converges. Either one's totally acceptable because it's not clear what we're being asked in this case. Is it absolutely or just, convergent? Absolutely convergent just means that when it doesn't alternate, it still converges. It's a quote-unquote stronger form of convergence, and that concept does not come up in Calc BC. All right, let's look at the next thing. If the sum from 0 to infinity of a sub n converges, what can we say about the sum from 0 to infinity of -1 to the n, a sub n, over n squared plus 9? All right, so if the n squared plus 9 wasn't there, we would be able to say that -1 to the n, a sub n converges absolutely, right? Because we already know that a sub n converges. I probably should have put in this problem. In my mind, I'm thinking it, that a sub n is greater than or equal to 0 for all n. But I didn't write it. But let's assume that I did write it because that's how I've solved the problem. Like, that's the context that we're working in. So what I'm going to do is I'm going to say that a sub n over n squared plus 9 is less than a sub n, which is definitively true. And so then we know that the non-alternating version, which is just a sub n over n squared plus 9, converges by direct comparison because we know that a sub n converges. And then, well, actually, I guess the argument that I'm finally making is like the overall argument anyway. The sum from 0 to infinity, negative 1 to the n, converges absolutely, right? Negative 1 to the n, a sub n, n squared plus 9. That's going to converge absolutely. I don't like this problem. I think it's a bad problem. I apologize. I mean, it's a good idea to think about at some point, so I don't apologize sincerely, but I do kind of apologize. All right, let's take a look at the next one. If you're going to write hundreds of problems, some of them aren't going to be good, and this is one. Number 3, let f of x be the function satisfying f of negative 2 is 6, and having the nth derivative at x equals negative 2 for n greater than or equal to 1. So that's important, though. N is greater than or equal to 1, which means this does not apply. This formula up above does not apply for n equals 0, which is the value of the function, which we were already told was 6. So keep that in mind. Like, the value of the function is 6, given. All right, so we want to use a third-degree Taylor polynomial to approximate f of negative 1.9. So we're going to need to write it. So what I'm going to do is figure out the nth term of this thing. So the nth term of a Taylor polynomial is going to be the nth derivative x minus a to the n over n factorial. So we just happen to know the nth derivative at negative 2 is this weird thing, right? So it's the nth derivative at negative 2, which is the given thing. And then it's times x minus negative, so plus 2 to the n over n factorial. This simplifies like a tiny little bit because n plus 1 factorial is n plus 1 times n factorial, and then you can cancel the n factorials. So negative 1 to the n, x plus 2 to the n, I'm sorry, negative 1 to the n plus 1 that's left over, x plus 2 to the n over 3 to the n. All right, so to write our polynomial, what we're going to do is take the value of the function, which we know is 6, that's given, and now we just have to say plus, what is the first term? What do we get when n is equal to 1 and we plug into this thing? Well, we just get negative 1, we get 2, we get x plus 2 to the first, and then over 3 to the first. So negative 2/3 x plus 2 to the first. Then we're going to plug in 2. So that's going to give us plus 3 over 3 squared x plus 2 squared. And we're doing third degree, so we're going to plug in 3. That's going to give us minus 4 over 3 cubed x plus 2 to the third. So that's how you do these. They look a little weird, and I don't know if they're intimidating or not, but they look weird. I think of them as just being annoying, to be honest. Now we're just going to plug in negative 1.9. We're not even going to simplify it, though. Negative 1.9 plus 2 is just 1/10. So I'm just going to rewrite that as 1/10, and I'm going to leave it to powers. I'm not going to do anything with that. Like this. And this, well, that's a mistake. That's supposed to be 27. Hold on. Hold your horses. I guess I'll fix it. I'm going to fix it in a different color, though. Shouldn't even have simplified it. These are the prices you pay for trying to simplify things. 27. There we go. Okay, that's the entire problem set. So I hope this was helpful, and good luck.